Okay, Doc. You know what happens when people double-cross the boss.
They go bowling?
Nah. They usually get a pair of cement shoes to go sleep with the fishes. But seeing as though we is out of cement, I figure this kiddie bowling ball here would do just nicely.
Well, actually, I don't think a bowling ball will...
See, Doc.
I've been spared!
Why do some things float while other things sink? How is it that a steel barge full of cargo can float, but a piece of steel by itself would sink to the bottom of the river? Archimedes asked questions like these centuries ago in ancient Greece, and his discoveries hold true even today. Plan to understand how Archimedes' principle allows us to move above, below, and within the Earth's fluids on this edition of Project Epiphany. Archimedes stated,
"The weight of the fluid displaced by an object equals the buoyant force on the object."
Now, as usual in science, a principle like this one is packed with information. As you can see, some of the words in the principle are highlighted, each of them important in learning why something will sink or float. So let's get started.
Wait!
The universe is mostly empty space called a vacuum. All the stuff in the universe that isn't space is made of matter. Stars, planets, people, ferrets, beach balls, even that plastic nubby thing on the end of your shoelaces. It's all matter. The amount of matter in each of these objects is called its mass, and we use a balance to measure it. The balance measures in grams. A gram of matter is about that of a thumbtack. Now here's an empty party balloon. The balance reads
11.7 grams!
Now let's put some air inside and take another measurement.
15.8 grams! That's a difference of 4.1 grams!
As you can see, the air inside has mass. Everything, even the air we breathe, has mass. Sir Isaac Newton tells us that there is a force of attraction between all matter. He called it gravity. Gravity is the force that can be found between any two objects. This means everything is being pulled on by everything else in the universe. This sounds like a science fiction movie where you could cause objects to fly to you on command. Ah! But in reality, things attracted to us are more attracted to the Earth. Newton says you're attracted to the sun, but when you jump into the air, you fall back to Earth. This is because even though the sun is more massive than the Earth, it is too far away to pull you from Earth's gravity. We can calculate the amount of gravity using Sir Isaac's equation. For example, the mass of the Earth will go here in the equation, and the mass of the sun here. The distance between the sun and the Earth goes on the bottom of the equation. Let's look at what happens if we change things around. If the mass of one of these objects goes up, so will the gravity between them. If the objects get further apart, the gravity between them gets weaker. Sometimes it gets so weak that we say you're in zero gravity.
It's probably not true that there's absolutely zero gravity in space. Gravity is a force that arises from large masses. The mass of the Earth has a gravitational pull, and that pull is a force. As we get further and further and further away from the Earth, that pull is lower and lower and lower. Now, if we were to continue to go out in space and start getting close to Jupiter, okay, then we would begin picking up the gravity of Jupiter, because it's a larger mass. That would actually be a greater pull.
Usually we talk about the gravity between you and the Earth.
You have mass. The Earth has mass. So therefore, there is gravity. If we stick a bathroom scale between you two, it measures the force of gravity on you. And we call this force your weight.
The mass of this pin is how much matter is in this pin. This is 100 grams whether or not I hold it in my hand here, or I carry it to the top of Mount Everest, or if I take it out into space. It's still 100 grams. Weight, however, is a measure of the pull that the Earth has on us. Its weight is greater here than it would be on Mount Everest than it would be in space. Essentially, it would weigh almost zero in space.
Time for review. When we talk about the weight of something, we are describing a force and not a mass. All matter is made of mass, and all masses are attracted to each other. This force of attraction is called gravity. The force of gravity between two masses is called the object's weight. Usually one of these masses is the Earth. The other could be you, a boat, hot air balloon, anything. All of these things have weight because they are attracted to the center of Earth. Okay, so now we know what weight is. But in order to understand Archimedes' principle, we still need to go over 3 other terms.
Fluid.
Objects float in fluids. So if we want to understand floating, we first need to understand what a fluid is. Fluids, along with all other matter, are made of particles, and they're always moving. Particles dart around, bumping into each other in their containers. They move faster and spread out when heat is added to them. Typically, matter on the Earth is found in one of 3 states: solid, liquids, or gases. The particles of a solid are usually moving very slowly and are very close together. A solid is not a fluid because it cannot change its shape to fit its container. If enough heat is added to a solid, the particles will be moving fast enough and far enough apart to melt and now be called a fluid. Liquids are a type of fluid. They're called fluid because they can change their shape to fit their container. Heating up a liquid will cause the molecules to move even faster and spread further apart. With enough heat added, a liquid will boil into a gas. Gases are fluid not only because they can change shape, but they can change size.
Gases tend to expand greatly. And they can do a couple of things. If they're in a volume like a balloon and you went and heated a balloon, the balloon would begin to expand. If you had a bottle like this that was sealed up and you heated it, and it was just full of gas and you heated it, what's known as the pressure would increase. If you took the cap off, all of a sudden the gas would just blow out, the hot gas would blow out.
We say that both liquids and gases are fluids because they have the ability to change their shape. Fluids move around objects when they come into contact with them. Water flows around a paddle. Air flows over a car. If fluids didn't flow, we wouldn't be able to move at all. And don't forget that humans are mostly made of liquid water. If fluids didn't flow, we couldn't exist.
Because this is a fluid, everything that is horizontal to the Earth, or to the gravitational force, is at the same pressure. Think of pressure as a force. Okay, it's really force per area, but think of it as a force. So the pressure here at all points at this level are the same, okay? However, as we move up, the pressure is lower. As we go down, the pressure is higher.
Imagine you were the size of a molecule at the very top of the atmosphere, where air is extremely thin, and there's nothing above it but the vacuum of space. As you drop towards Earth, there would be more air above you. This air is pushing down on you because it's attracted to the Earth. and you're between them. This means the air pressure is increasing. Lower altitudes get higher and higher air pressures because there's more air above you to press down. Now let's go under the water a bit. To determine the pressure here, you need to think about what's above you. Not only do you have the entire atmosphere of air on top of you, but now there's water forcing on you as well. The deeper underwater you travel, the more water on top of you. In fact, the bottom of the ocean has more than 1,000 times the pressure than at the surface. So what do we need to know about fluids? Matter is most often found in one of three states: solids, liquids, and gases. Liquids and gases are called fluid because they can flow and change shape to fit their containers. The more matter above you will increase the pressure on top of you. So far, Archimedes' principle says the weight of the fluid. Because fluids have mass, they're attracted to the earth and have weight. A waterfall is a beautiful example of fluids having weight. If water had no weight, well, it wouldn't fall. A gust of wind can do a lot of damage. If air was weightless, it couldn't force anything anywhere. And now we know about the concepts of weight and fluid. 2 down and 2 to go.
Displaced.
From the day we are born, we start exploring. We find out that water takes the shape of a bathtub. Water moves when we're in it, or when we splash with our toys. Whether the toy floats or sinks, it doesn't matter. Everything that goes in the bathtub makes the water level rise. But the same is true for any fluid, not just in a bathtub. As these drag boats speed towards the finish line, they're actually raising the water level in the lake. Fluids change shape when something pushes on them. We say that it's being displaced.
The force of this object is its weight. You know, if I drop it loop on the table, it's got a force, okay? So if I drop it in the water, the force or the momentum of that object is enough to literally push the molecules of water out of the way.
Everything takes up space, but not the same space. If the hippo wasn't swimming, water would be in its place. If this balloon wasn't here, cool air would fill its space. But as it is, both the hippo and the balloon are displacing fluid. The question we need to ask now is, how much fluid is being displaced by these objects? Scientists call the space an object takes up its volume. For example, the volume of this container is 1 liter. It's simply a cube, measuring 10 centimeters on all sides. By multiplying the length, width, and height, we can find out the cube's volume. 10 centimeters times 10 centimeters times 10 centimeters equals 1,000 centimeters cubed. It's also called 1 liter. Inside the cube now is 1 liter of air. But if I pour a liter of water into this container, the air will be pushed out. We say it's displaced. This happens because two things can't be in the same place at the same time. Measuring the volume of a cube is pretty easy, but most things are oddly shaped. Think about all the curves that make up a hot air balloon, or the bottom of a canoe, the body of a fish, or a person. The volume of these things would be nearly impossible to find with just a ruler. In ancient Greece, Archimedes was able to figure out a way to measure the volume of just about anything, regardless of its shape. It's the 3rd century BC. Hero II, king of Syracuse, has called for the royal goldsmith to take on a very special assignment. I want you to make a crown worthy of the king. Namely, me. Yes, sire. It would be my honor. Here is the amount of gold I will give you for the crown. See to it that all the gold is used. Yes, sire. I can't wait to take this gold into town. What did you say? Oh, I said, I can't wait to make this gold into your crown. When the new crown arrived, King Hero felt that something was wrong and went to find Archimedes. He was a man who could solve many problems, but most of all, could be trusted by the king. Archimedes, I have a job for you. I need to know if I've been cheated in the making of this crown.
Yes, sire. I won't do anything until I find the answers you need.
In the vaults, he found an identical chunk of gold.
First, let's see if they weigh the same.
Sure enough, the crown and the chunk of gold were the same weight. But something still didn't feel right about the crown.
A crown this size should be heavier than this. But how do I prove it?
Archimedes thought, and thought, and thought some more. The days went by in his workshop, thinking day after day after day, and soon he began to stink. His servants drug him off to the bathhouse. And as he got into the water, he noticed that the water level rose.
Eureka!
Forgetting his robe, Archimedes ran down the streets of Syracuse back to his workshop. He took the chunk of gold, submerged it in a tank, and measured the displaced water level. He did the same for the crown. The crown displaced more water than it should have if it were solid gold. Remember, they had the same mass, but they ended up with different volumes. They could not both be solid gold. We use this same technique to determine the volume of objects. The water level will rise by the same volume as the object. When this toy is submerged, it raises the water level. A little subtraction tells us that the toy has a volume of almost 30 milliliters. Displacement sounds like it should be an easy concept to master, but every Thanksgiving, many people lose their possessions because they don't think about Archimedes' principle.
We've recently tested several models of deep-fat turkey fryers and find that this method of cooking can be very hazardous.
Looks like our partially frozen turkey is ready. The temperature's at 350 degrees, so put the turkey in.
Units can be overfilled, and when that happens and a turkey is added, the oil spills out, causing the unit to catch on fire. If you overfill a deep-fat turkey fryer and add a turkey, the oil can spill over the side and ignite, causing a severe fire hazard. We hope everyone thinks twice before using a deep-fat turkey fryer, but if they do, they should exercise extreme caution. Always use these units outdoors, never on a wooden patio or in a garage. They should always be placed on a flat, level surface and never should be left unattended.
So what do we need to know about displacement? It boils down to the fact that no two things can be in the same place at the same time. The amount of fluid pushed aside will equal the volume of the object. It's also good to know that Archimedes discovered the relationship between mass and volume. Okay, 3 of the 4 terms are finished. But before we move on, Archimedes' experiment with the mass and volume of gold has led us to another very significant concept: density. Density
is a measurement of the mass of an object divided by the space it takes up. This easy calculation is a way of identifying and separating substances. Silver and gold have different densities. That means in order to have the same mass, silver has to have a greater volume. The king's crown was probably silver and only plated gold, and that's why it took up more space than it should have. Every substance has its own density. Smaller densities rise to the top, while greater densities sink towards the bottom. Ice sinks in alcohol, but in vegetable oil, it floats. Notice that when the ice melts into liquid water, it sinks below the oil. Fluids order themselves according to their densities. Pure water has a density of 1 gram per milliliter, because 1 milliliter of water has a mass of 1 gram. It's the most common substance on the planet, and it's no coincidence that it has a simple, easy to remember density. The metric system was designed with water in mind. Densities greater than 1 will sink in water, while those densities that are less than 1 will float. Not all things sink at the same speed. We can estimate their densities by comparing how quickly they sink. The cubes on the right are more dense than the cubes on the left, but they are all greater than 1. How much of these objects are floating below the surface of the water? If we estimate the percent of the object under the water, it will tell us the object's density. This wood floats so half of it is below the water. That's 50%. So it should have a density of 0.5 grams per milliliter. Styrofoam floats much higher on the water than wood typically does. How much do you see below the surface of the water? What would the density be? 0.01 is much less than 1, so styrofoam floats. What would you expect from a piece of wood and a rock? Surprising? This exotic piece of ironwood is one of the few trees in the world that produce wood more dense than water. Pumice is an igneous rock, which means it's produced from volcanic activity. As the rock cooled, air was trapped in pores. As a result, the density is less than 1, and it floats. Keep that in mind if you're ever shipwrecked near a volcano.
My name's Jim Lovins. I'm the senior aquarist at the St. Louis Zoo, which means I take care of all the aquatic animals here. Pretty much like all animals. I'm kind of partial to our big catfish in here, Mambo. She's about, probably closing in on 100 pounds. Most fishes have what they call a swim bladder. It's actually an organ that's inside the gut area of the fish, and the fish basically has this inflated with gases. And it's the same gases you and I breathe. There's nitrogen, oxygen, carbon dioxide, but it kind of makes it like a balloon, because obviously, you know, there's some weight to the animal.
Air takes up a lot of space, while only adding a little mass. This makes the fish less dense.
Well, just like any other organ, it can have diseases or viruses, lots of things. Just like a human lung, it can fill with fluids. The animal would spend a lot of time on the bottom. It would work very, very hard to try and get itself to the surface, or even to swim to get food or escape something.
But not all fish use a swim bladder.
Only some of the most oily fishes in the world all come out of the sea. And as you know, oil is much lighter than water also. So it's able to make itself more buoyant because of the oils in its body.
It takes this guy a bit more effort to swim down to the bottom.
Good comparison. Yeah. Well, obviously turtles don't have that buoyancy control device. They do have lungs, so by getting a breath of air, they're going to be more buoyant. So they'll have more difficulty swimming to the bottom. Another thing they'll have with the swim bladder is maybe they've expelled air from their swim bladder, and that can happen from like a high impact. I mean, you don't think of fish as falling, but imagine a waterfall. It'd knock the breath out of you, right? Well, kind of the same with them.
If a fish loses air, it becomes more dense and has to hang out at the bottom for a while. A submarine is man's improvement on the swim bladder. Instead of filling up with air, a submarine has chambers that fill up with water. As the heavy water rushes in, the boat becomes denser than water and sinks. When the captain wishes to surface, A submarine can force the water back out into the ocean, making the sub light enough to rise. Density is a term we give to describe how much stuff is in a given amount of space. Higher density objects are found below low density objects. A hot air balloon must be less dense than the air in order to float. Water is denser than air, which is why we find the ocean below the atmosphere. A fish has a density very close to water, so it doesn't float or sink, but hovers where it wants to. And a chunk of concrete or steel has a density much greater than water, so it sinks to the bottom. The weight of the fluid displaced. Archimedes determined that the weight of the water displaced by an object is the key to floating. We can measure this by first weighing an empty container for catching water. We'll need this for later. Now, gently drop an object, like this child's bowling ball, into the fluid and be careful not to spill any. As you know, the water level rises because it's being displaced. Using this fancy piece of equipment called an overflow container, you mean a bucket with a hole in it? Yes. We can catch all of the fluid that's pushed out of the spout, down to the last drop. Finding the displaced fluid now is just a matter of reading the scale. One problem though, the scale is reading the water, but it's also measuring the bucket. This is why we measured it empty, by itself first. We only want to know the weight of the fluid displaced, so we subtract off the weight of the bucket. The weight of the water pushed aside by the bowling ball will help us understand why it floats. Now we know about weight, fluid displacement, and a little density too. On to the final hurdle in understanding Archimedes' principle.
Buoyant force.
A force is a push or a pull. As you sit and watch this program, there are forces acting on you. Gravity pulls us down towards the center of Earth, and the chair supports us with an upward force. And without this upward force, you would fall to the floor. Notice that the forces are the same size. We say that the forces are balanced. It's like a constant game of tug of war. If the forces are balanced, then the rope won't move in either direction. When one team pulls harder than the other, the forces become unbalanced. Only then does the rope move. In fluids, there's a battle between forces as well. Gravity forces downward, but without another force to balance it, everything would sink. We need an upward force to work against gravity and keep things afloat. This is called a buoyant force.
So the weight of this object comes into play. Okay, so that's the first part of Archimedes' principle, a weight of an object. So it's the weight of this object. Why is it important? Because the weight is related to how much gravity is pulling down. That's a force. That's the downward force. The upward force is the buoyancy force. And what the buoyancy force is, it's all the pressure that's acting on the bottom of this vessel, pushing it up.
Let's prove there's a buoyant force by weighing a brick. As any object is lowered into the water, it gets lighter. The water is forcing up on the brick and cancels out some of its weight. This is the buoyant force in action. But even though it's lighter, it's not light enough to overcome gravity. The brick sinks. So where does a buoyant force come from? Just like your chair holds you up, fluids have the ability to force back on the matter that's sitting on top of it. Consider some water along this line near the surface. Water and air force down on this point just like when you sit in a chair. The water at this level must push back with the same force. As we go deeper, there's greater weight sitting on the water. So the water at this level has to push back with equally greater forces.
See how the forces get larger the deeper we travel? The USS North Carolina. Finished in 1940, it was the first of many modern battleships. Longer than 2.5 football fields from aft to stern and over 100 feet wide, this seasoned battleship was a key player in the war against Japan. Primarily built from concrete, steel, and wood, the North Carolina housed over 57 guns, a seaplane, and more than 2,000 sailors. Fully loaded with fuel and water for its boilers, the North Carolina weighed in at a staggering 46,000 tons. The massive weight of this battleship would be a significant force downward on the water. And the forces near the surface of the water would not be enough to hold up a ship of this size. This is why we never see battleships floating like styrofoam on top of the water. The boat will sink until an equal force can hold it up.
What will happen is, as if an object is heavier, more fluid must be displaced, and typically that means the object will have to go deeper in the water.
The North Carolina displaces 46,000 tons worth of water in order to float. Now, a lighter object like this 4,000-pound seaplane will only have to push aside 4,000 pounds of water in order to float. Make sure you see the relationship. As an object displaces more water, it has a greater buoyant force acting on it. Archimedes' principle states that the weight of a fluid displaced will equal the buoyant force on an object. The following demonstration is used to prove this principle to be true. Remember the brick from before. It had a buoyant force of 7 newtons. We calculated that by looking at the difference in its weight above and below the water. Now let's do the same experiment, but this time catch all of the displaced water. Look, the brick pushes out 7 newtons of water. Archimedes' principle is correct. The weight of the water displaced equals the buoyant force on the brick. Archimedes' principle says that in order to float, an object must displace an amount of fluid equal to its own weight. A ball of clay doesn't displace enough water to float, but watch as these students transform the clay into a shape that can sit deeper in the water. Oops, not enough water was displaced that time. Ah, much better. These boats are deep enough in the water to float. Shape is everything. As we have seen, even concrete and steel can be shaped into a floating battleship. Think of it this way. When a hippo pushes water aside, which is heavier, the hippo or the water? The force of the hippo down is greater than the water pushing up, so the hippo sinks. A fish should displace water equal to its weight in order to hover within the water where it chooses. And the USS North Carolina is obviously not completely underwater, but the water that is displaced must weigh the same as the ship. Which of these barges on the Mississippi River has more cargo on board? We can tell just by looking at them. The heavier barge is the one deeper in the water. Heavier objects must displace more fluid to get a bigger buoyant force. When a boat takes on more weight, it lowers into the water. Eventually, the ship runs out of hull and starts to take on water. This water adds more weight. In order to stay afloat now, the ship must sink deeper into the water, which lets in more water, which adds more weight. So the ship lowers into the water and takes on more water weight. The physics of sinking are hard to overcome once the cycle has begun. Now, some canoes have styrofoam in their tips, which makes it very difficult to sink. These boats can still stay afloat even when filled with water and people. Swamping a canoe can be a lot of fun, but it isn't very easy to paddle.
Now here's kind of interesting. When you and I stand on a bathroom scale, depending on how big we are and how much, there is a buoyancy force associated with the atmosphere. We are displacing air.
So just by being here, you have a buoyant force equal to the weight of the air you push aside. Obviously, no human has a buoyant force large enough to fight off gravity and float. But a hot air balloon does. A balloon must displace cold air to rise. It must move aside more cold air than the basket, people, fuel, material, and the hot air inside it.
So how do these things fly?
How do they fly? They fly by basically having hot air. Hot air goes into the balloon and it rises. The more you heat up the balloon, the more it wants to rise.
The pilots warm the air in the balloon with fire. As the hot air spreads out, it becomes less dense. Some air is pushed outside of the balloon, and less air means less weight.
The envelope itself weighs about 350. The basket fully loaded with fuel is about 450, 475.
When the balloon, basket, people, and fuel are added, the total is still less than the cold air that was displaced. And away they go, buoyant forces winning out over the force of gravity. Gently gliding where the winds take them on a beautiful summer afternoon. It's too bad Archimedes never had the opportunity to witness his principle take to the skies.
Eureka!